Everyone, welcome to Hugh Ross's Paradoxes class. We're going to begin now. We thank everybody for showing up. We thank everyone who's out there in the YouTube land for showing up as well. We're going to, as we usually do, let everybody know the restrooms are off to my left, and there's signs showing you how to get there. We thank you to Hugh Ross for bringing in the sandwiches. Thank you, Hugh, for bringing the sandwiches again. We appreciate that. And there's other goodies as well. Other people are going to be coming in, so we'll just let them do what they're going to be doing. Welcome, friends. It's good to see you again. This remains on YouTube, and so this is going to be recorded. So yeah, so I just want everybody in the room to know that you can get it on YouTube. And with that, the only other thing I want to mention is if you have a cell phone with you, please set it on stun so it doesn't set off alarms while we're talking. Yes. So Hugh, with that, please come on up and take over.
Sure.
Thank you.
Well, you can tell that Mark used to work for the LAPD. He calls that a stun. So, well, let me begin by just sharing what's coming up in the next few weeks here in the Paradoxes class. I'm going to try to finish this series we've been doing on whether or not we humans are alone in the universe. We've already covered what the Bible's going to say about it, then wrapped up what the Book of Nature's got to say. But after that, I'm going to be launching a short series, on the creation of the elements for life. And then I've got Ken Samples lined up, our staff philosopher here at Reasons to Believe. He's going to be doing a short series on what he thinks and what he believes is the most compelling historical evidence for the bodily resurrection of Jesus from the dead. And then we've got Fuzzrana coming in after that as well. So with that, let me get started here. Okay. Last week we kind of ended up with what the universe has got to say about whether or not we're alone, and what the solar system's got to say. But basically we're talking about testing for exohabitability. Is it possible that we're ever going to find a moon or a planet that has the possibility of being able to sustain creatures like ourselves? So human beings, or functional equipment, creatures that are subject to the laws of physics and the space-time dimensions, with the capability of launching and sustaining high-technology civilization. Now, if you really want a thorough treatment of this subject, more than what I can give in just these 3 talks, I'm coming out next month with a book called Design to the Core. And then you can also get this book, The Creator and the Cosmos, and anyone can get a free chapter of that book by going to reasons.org/Ross. So last week we ended up on what the whole universe has got to say. And as Mark announced, if you missed last week or the previous 2 weeks, you can get caught up by going to paradoxes.org. All these sessions are recorded, and so you can watch it or you can listen to it. But what I want to do now is go from the universe as a whole down to a super galaxy cluster. And a super galaxy cluster is a cluster, it's clusters of galaxies. So typically a supercluster of galaxy will have anywhere from a dozen to several dozen clusters of galaxies in it. And only recently have we astronomers been able to define a supercluster of galaxies. It's basically a grouping of clusters of galaxies where they're gravitationally bound to one another, where these clusters of galaxies are moving towards a center of mass within that. Now, that also means they take out the definition of the expansion of the universe. Most superclusters of galaxies are not collapsing. The expansion of the universe causes them to disperse, but what astronomers do is they take out the cosmic expansion velocity for every supercluster of galaxy and say with that removed, then are these clusters of galaxies coming together, or spreading apart. So we're looking at what are called the peculiar velocities. A peculiar velocity for a star, a galaxy, or a cluster of galaxies is where they subtract out the velocity that's due to the expansion of the universe. Now, these are a couple of images of superclusters, and astronomers now recognize that there's about 2 trillion galaxies within the observable universe. So whenever we do deep sky observations, we see way more galaxies than we do stars. So for example, in this particular image, everything you're looking at is a galaxy except for 4 stars in our galaxy. Say, how can you pick out the stars? Well, the stars are point sources. They're in our galaxy, and you can tell the stars because you'll actually see some of the mounting for the secondary mirror. So for example, if I were to go over here and pick out a star for you, this is a star. Notice you can see the mounting for the secondary mirror. That's also a star. This is a star, and there's one other thing over here. Those are the 4 stars in the image. Everything else is a galaxy. And you can see some of the galaxies are large, some of them are small. This is the famous Hubble Ultra Deep Field, where they let the Hubble Space Telescope integrate the light over 2 weeks on a patch of sky that was 1/15 the diameter of the moon. So they just had that Hubble Space Telescope stay on that patch of the sky and just absorb all the light that comes in. And the longer the exposure, the deeper you can see into outer space. And in this particular case, only 3 stars in this image, or only 3 objects in this image are stars. Everything else is galaxies. Now, a couple of years ago, a team of astronomers actually mapped the super galaxy cluster. It was only like 6 years ago, astronomers could even define what a super galaxy cluster is. But shortly after that, they actually produced a map, and this is a good chunk of the observable universe, and every little point of light there is not a galaxy. It's not a cluster of galaxies. It's a supercluster of galaxies. So even the tiniest points of light you see in this image are superclusters of galaxies. And the little red dot that you see there, low center, that's where the local superclusters are. And so here we're mapping most of the observable universe. And what I'm going to do in the next slide is zoom in on that red dot. And we zoom in on that red dot. This is what you see. This is a 3D map of the local super galaxy clusters. And again, every kind of patch that you see there is a super galaxy cluster. And the little red dot basically identifies the super galaxy cluster that we're in. So, tens of thousands of super galaxy clusters in the universe, and we're at one marked by the red dot. But what astronomers have discovered doing exhaustive surveys of these superclusters of galaxies, we live in a unique supercluster of galaxies. So people say, advanced life and all those different trillions of stars. Well, we can now say confidently, if you want to have advanced life, it has to be in a particular kind of super galaxy cluster, and we're living in the only one that we know of that has the just right features. So for example, this is what's now referred to as the Laniakea super galaxy cluster. And it kind of has the shape of a stick insect. Most of the clusters of galaxies are distributed along long filaments. And what you notice here is that you've got 4 big clusters of galaxies in the Laniakea. You've got the Centaurus cluster over to the extreme right. You've got the Virgo cluster, which is just left of that. And then down to the bottom, you got the Fornax cluster and the Hydra cluster, kind of at the, I mean, this kind of looks like a dog, right? And so at the front paw and the back paw, you got the Fornax, and the Hydra clusters. But that little red dot basically identifies our local grouping of galaxies. And so the Laniakea supercluster is composed of large clusters of galaxies and then we call groupings of galaxies. And we live in the smallest grouping of galaxies in the local supercluster. And what I'm going to do in the next few slides is show you what the rest of the nearby superclusters of galaxies look like. But the bottom line is we're living in the only one where the clusters and local grouping, or the groupings of galaxies are strung out along these long filaments and subfilaments. Matter of fact, our local group is at the nexus of 3 subfilaments, not on a filament. I mean, you've got a filament going down towards the Fornax cluster, a long filament going down the Hydra cluster. There's a filament that goes above our local group, but where the local group is, we're at the nexus of 3 tiny subfilaments of the filaments. But this Shapley supercluster is what most super galaxy clusters look like, where the clusters of galaxies are jammed tightly together, and in this case, the galaxies and the galaxy clusters and local groups are all very densely situated inside what's basically a football-shaped or ellipsoidal-shaped superclusters of galaxies. And what you notice here, there are filaments here as well, but the filaments are all so close together, the galaxy clusters are jammed so tightly together that it's not possible to have a galaxy there that's not being exposed to a supermassive black hole that's radiating out deadly radiation, or where they got nearby giant galaxies that'll be disturbing the structure of the galaxy. And that's a requirement for advanced life. You need to be living in a galaxy that's not being gravitationally disturbed and is not being subject to deadly radiation. That's simply not possible anywhere within the Shapley supercluster of galaxies. And incidentally, we had a member of the class, the son of Harlow Shapley, over whom this super galaxy cluster is named after. And I remember when I first was teaching this class, and he walked into the class, he was a spitting image of his grandfather. So as an astronomy student, I had to study Harlow Shapley's works, but they named the super galaxy cluster after him. This is the Perseus Pisces supercluster, not quite as dense as the Shapley supercluster of galaxies, but nevertheless, the clusters, you can see there's one long filament here, and all the clusters of galaxies are either aligned on it or along filaments that are perpendicular to it. But once again, there's no room within this supercluster of galaxies to have a galaxy that's not going to be gravitationally disturbed or exposed to deadly radiation from a supermassive black hole. Now, I'm not saying that you can't have microbes existing in these super galaxy clusters. Again, the subject of this series is, are we alone as the only advanced physical species of life that is intelligent and capable of launching and sustaining global high technology civilization? So yeah, I'm not ruling out places where microbes could exist, but we are seeing conditions. Here's the Leo supercluster of galaxies. And again, this one is quite a bit smaller than the Shapley supercluster of galaxies. But even here, the galaxies and galaxy clusters are simply just too close together, too densely packed. And here's one of the most densely packed superclusters of all, the Ursa Major supercluster of galaxies, where you can see that you got these gigantic clusters and clusters of galaxies, again, very densely packed, not permitting any place. And so kind of looking at that and comparing it with the Laniakea supercluster of galaxies, I think you can see it's like night and day. Living in a super galaxy cluster that doesn't look like any other super galaxy cluster that we know. And as I mentioned, we're not even a filament of this super galaxy cluster. we're at the nexus of 3 small subfilaments. And for that reason, we live in a unique grouping of galaxies. I should have added a slide here. It will be in my book, Design to the Core, where I show our grouping of galaxies compared to all the local grouping of galaxies. Bottom line, we live in the only grouping of galaxies that has only 2 large galaxies in it. All the others have several large galaxies, even giant galaxies. But this is a map I made of our local group of galaxies. And what's unique about it is that it has only 2 large galaxies in it. And the 2 large galaxies are far apart. If I were to show you slides of other groupings of galaxies, they have large galaxies, but they're close together. What we see here is you've got the Milky Way galaxy at the lower right, you've got the Andromeda galaxy at the upper left, and they're far enough apart that the supermassive black hole in the Andromeda galaxy doesn't really affect advanced life. Now, that wasn't always the case. The supermassive black hole in the Andromeda galaxy, upper left, weighs in at 140 million times the mass of our star, the Sun. Fortunately for all of us in this room and all of you watching on YouTube, this supermassive black hole in the Andromeda galaxy currently is in a quiet phase. What makes these supermassive black holes deadly is when they're absorbing matter. When they're absorbing matter, as that matter begins to come close to the event horizon of the supermassive black hole. If you missed what we talked about event horizons of these supermassive black holes, but when they get close to the event horizon, the energy conversion out there is extremely efficient. A minimum of 10 to a maximum of 42% of the incoming matter gets converted into pure energy. And that energy is deadly for advanced life. But fortunately, the supermassive black hole in the Andromeda galaxy is only some pieces of matter towards it. And fortunately, we live in a large spiral galaxy that has a tiny supermassive black hole. Tiny, it's 4 million times the mass of our star, the Sun. Doesn't sound tiny, but compared to what you'd expect, the Andromeda galaxy has a normal-sized supermassive black hole given the mass of the galaxy. Both the Andromeda galaxy and our Milky Way galaxy come in at about 1.25 trillion times the mass of our star, the Sun. Now, that's an important feature for advanced life. If our galaxy were any smaller, then it would be gravitationally disturbed by adjoining galaxies. But it's big enough that it can fend off the gravitational disturbances of nearby galaxies. So yeah, you don't want it to be any smaller, but if we're any bigger, then our supermassive black hole would be more massive. Now, fortunately, we're living at a time when the supermassive black hole in our Milky Way galaxy, as is the supermassive black hole in the Andromeda galaxy, are in a quiet phase. We know both of them have been in a quiet phase for the past 2 million years. And what I mean by quiet, they're not eating any stars. If they were to eat a star, you would get a huge blast of deadly radiation. They're not even eating planets. They're not eating moons. What they're consuming are objects the size of comets and asteroids. And so astronomers are continually observing the supermassive black hole in the center of our galaxy, and they're literally seeing flares every few hours. And the flares are caused by the supermassive black hole gobbling up a comet or an asteroid. But because they're only gobbling up comets and asteroids, even though they're doing it several times per day, there's no deadly radiation that would pose a problem for us human beings. But there were times in the past, and I'll show you a slide of this a little bit later, where our Milky Way galaxy was actually consuming bigger objects. And when that happened, that would have been a problem for us, but not a problem for relatively primitive life or even for plants. Plants can survive a lot of radiation exposure. Certain small mammals can as well. Where it becomes a problem is where you've got a large-bodied species of life with a huge amount of protein in it that needs to live for decades. I mean, it's different if you're a dog. A dog lives 10 years, and so it can tolerate a lot more radiation exposure. But if you want to have the equivalent of human beings that can live 80 years, they have to be living in a low radiation environment. And we've been in a low radiation environment for the past 2 million years. Now what you see in this map of our local group, you've got the Andromeda Galaxy, you've got the Milky Way Galaxy. The galaxy off to the extreme left, that's the Triangulum Galaxy. It shows up right here, but it's actually the fourth most massive galaxy in the local group, and it's classified as a dwarf galaxy. It's a dwarf spiral galaxy. And if you look down towards our Milky Way galaxy, you can see the large and small Magellanic Clouds. The large Magellanic Cloud is actually the third most massive galaxy in our local group. It comes in at 1/16 the mass of our Milky Way galaxy. Oh, actually, that's incorrect. It's coming in at 1/6 the mass. They used to think it was 1/16, but they now very carefully and accurately measured the mass by 4 different techniques. And so 2 years ago, they revised the mass of the Large Magellanic Cloud. It comes in at 250 million times the mass of our star, 250 trillion, pardon me, the mass of our star, the Sun, 250 billion times. Now, if you look again carefully at the Andromeda Galaxy, there's 2 dwarf galaxies, one to the right, one to the left. And so what I show here are the 5 biggest dwarf galaxies in the local group. But what dominates the local group are 100 and likely as many as 200 small dwarf galaxies. And if it wasn't for those dwarf galaxies, you wouldn't be in this room right now. In order for the spiral structure of our Milky Way galaxy to be sustained, it's important that it feeds on a regular diet of tiny dwarf galaxies. And that's one of the unique features of the local group. It's filled with tiny dwarf galaxies, lots and lots of them, but it has only 5 large dwarf galaxies and only 2 large galaxies and no giant galaxies. The fact that there's no giant galaxies means there's no, if you had a giant galaxy, it would be, its black hole would be deadly all the time. So that's not the case. But as we zoom in on our local neighborhood of the local group, here we see our Milky Way galaxy, and here you can see that the spiral arm structure is extremely symmetrical, and you really can't see any disturbance in the spiral arm structure except for you see what you see to the extreme right of that image. So highly symmetrical spiral arms. Then you see the large Magellanic Cloud and the small Magellanic Cloud towards the bottom. The masses of those 2 small galaxies, the large and small Magellanic Cloud, they're at just the right mass and have just the right location and distance relative to the Milky Way galaxy that they act as a funnel. They act as a gravitational funnel streaming in a regular diet of tiny dwarf galaxies. Astronomers refer to the large and small Magellanic Clouds as the dietitians for the Milky Way galaxy. They ensure that a Milky Way galaxy gets just the right diet of tiny dwarf galaxies to ensure that the spiral arm structure doesn't collapse. I mean, if our galaxy was not consuming these small dwarf galaxies, within 3 or 4 rotations, the spiral arm structure would collapse, and now you would have an ellipsoidal or a spheroidal galaxy. 94% of the galaxies that are relatively large are spheroidal, ellipsoidal. At one time, early in the history of the universe, 2/3 of the large galaxies galaxies were spiral galaxies. But once they stop consuming these tiny dwarf galaxies, the spiral structure collapses. And so today, spiral galaxies are a rare phenomenon in the universe. But what's exceptionally rare is to have a spiral galaxy with these highly symmetrical spiral arms. I'm coming up with a blog in a few weeks' time where I make mention of research that's been done in the outer part of our Milky Way galaxy, which basically establishes the last time our Milky Way galaxy ate a relatively large dwarf galaxy was 11 billion years ago. For the past 11 billion years, it has not absorbed a single large dwarf galaxy. It's only been eating these tiny galaxies, but it's been eating them at just the right rate, thanks to large and small Magellanic Clouds. Having a problem with this microphone again?
Yeah.
Okay, I'll use this. Okay, and then zooming in to our Milky Way galaxy. Again, this is the most detailed map. And just to remind you, this was not NASA's sending up a satellite way beyond the Milky Way galaxy and taking a photo. This is not a photo. It's a map that was constructed by astronomers looking at different parts of the Milky Way galaxy at different wavelengths. You cannot see the whole of the visible portions of our Milky Way galaxy from the Earth. There's dust clouds that block out. However, radio observations can see through those dust clouds. And therefore, by combining the radio images with the infrared images, the ultraviolet images, and the visible light images, astronomers are able to actually construct a fairly detailed, accurate map of our Milky Way galaxy. And this will be in my book, Design to the Core, but I write about how advanced life is only possible in a spiral galaxy that's got a bar at its core. And you can see there's kind of a bar-like structure at the core. That's essential. You need these highly symmetrical spiral arms, and you want not too many spurs and feathers between the arms. And that's a unique feature of our Milky Way galaxy. Very few feathers and spurs relative to what we see in other galaxies. And the spiral arms are just the right distance apart to make possible advanced life. What I'm going to show you in the next slide are the dozen galaxies that astronomers have found. Because just like as I was mentioning last week, astronomers have scoured the entirety of our Milky Way galaxy looking for a star that's sufficiently like our star, the Sun, to be a candidate to have a planet orbiting it, in which advanced life is possible. And after a 60-year search, they've yet to find a single star that sufficiently matches our star, the Sun, to be a candidate. Well, they've done a similar thing with galaxies. And so these are the closest spiral galaxies to matching the features of our Milky Way galaxy. The Andromeda Galaxy in the upper right here does make the list of the 12 closest. But if you look carefully at that, and by the way, you can see the two dwarf galaxies, one above and one below. But if you look at the spiral arm structure, you can see a significant warp in the structure. You also notice that the outer spiral arms are quite dominant compared to what we typically see in normal spiral galaxies. And an astronomer that volunteers for us here at Reasons to Believe, David Block at Witwatersrand University in South Africa, he published papers demonstrating that the dwarf galaxy, the smallest and most compact one that you see just above the core of the Andromeda Galaxy, it passed through the spiral arms of the Andromeda Galaxy 500 million years, and that's really what's responsible for the big warping of the spiral arm structure. And here are 6 more spiral galaxies. Probably the one that comes the closest to matching our Milky Way galaxy is the upper center one. Notice that the spiral arms are the most symmetrical of any we see besides the Milky Way galaxy, but you can see that those arms are distorted, they're exaggerated, and by the way, this galaxy is less massive than our Milky Way galaxy, and explains why it has suffered some gravitational distortions. But yeah, nothing comes really close to looking like our Milky Way galaxy. Now, in terms of where advanced life can exist, you can have microbial life in a fairly wide range of possible locations in our Milky Way galaxy, but not advanced life. Advanced life needs to be located close to what's called the co-rotation distance. So that red annulus you see there, that's the distance from the center of the galaxy where the spiral arm structure. The spiral arm structure for a Milky Way galaxy is rigid, so it rotates like this. But all the stars in our Milky Way galaxy obey Newton's laws of motion, which means the closer they are to the center, the more rapidly they revolve around the center. The farther away they are, the more slowly they go around. Our star, the sun, and a system of planets makes a revolution about once every 240 million years. But our sun is on what's just inside the co-rotation distance, and so we are revolving around the center of the galaxy at almost the same rate as a spiral structure, arm structure rotates, which means we get to stay for a long period of time at a safe distance between the spiral arms. Again, microbial life is possible when our solar system is inside a spiral arm or crossing a spiral arm. But if you want advanced life, you want to stay away from the dense molecular clouds and the supergiant stars that characterize the major spiral arms of our Milky Way galaxy. As you can see by the little yellow dot there, that represents our solar system. Right now, we're halfway between the Sagittarius and the Perseus spiral arms. Now, you say, wouldn't it be better if we were exactly at the co-rotation distance and therefore we would never cross spiral arms? The problem is if you're exactly at the co-rotation distance, you will suffer mean motion resonances. I'm going into the technical details, but the bottom line is if you get these mean motion resonances, it acts like a slingshot and kicks your star and its planets away from that zone at a considerable distance. So that's not a stable place to be. The best place to be is just inside the co-rotation distance, sufficiently inside that you escape those mean motion resonances, but close enough where you cross spiral arms very infrequently. And where we're orbiting right now, we cross a spiral arm about once every billion years. Now, in order to get all the heavy elements we need for advanced civilization, yes, carbon, oxygen, and nitrogen and phosphorus, those are the dominant, and potassium are the dominant elements that make up our body, but you also need zinc, you need copper, you need iodine in your body, and those elements require that your planetary system be born in the part of our galaxy where you got the heaviest enrichment of heavy elements. And this particular chart shows you where you're going to get the most intense. So that little dotted line there, that represents metallicity, by the way, is simply referring to elements heavier than helium. 98% of the elements in our Milky Way galaxy are hydrogen and helium. 2% are elements heavier than helium. But that dotted line shows you where you got the greatest density of these heavy elements. And we now know to explain why advanced life is possible on the Earth, we have to have our solar system form at that peak. But you don't want it to stay there, because that's one of the most dangerous spots in our entire Milky Way galaxy, because to get that density of heavy elements, that's also a place where the star density is very high, where you got gigantic molecular clouds, and so you do not want to stay there. You want to be kicked out. And astronomers now recognize that the solar system was born in the most dangerous part of our Milky Way galaxy, in a huge dense cluster of galaxies, and then it got kicked out. And how did it get kicked out? It's a gravitational slingshot. Just like when NASA sends a spacecraft to, say, Uranus or Neptune or Pluto, they take advantage of the gravity of Saturn and Jupiter to give it a kick, so they don't have to use as much fuel and they can actually get it there faster. So they actually time it to get these little gravitational triggers. Well, likewise, a clustering of stars, just right mass, just right distance, probably 4 stars, 5 stars total, were responsible for kicking the solar system out of its birth cluster, and then it got to a place where you see that second dotted line, that blue dotted line, and there again it encountered a grouping of stars that stopped the kick. And so it got kicked out and then it got braked, but it got braked at the best possible place for advanced life, where you actually have a low density of stars and a low density of giant molecular clouds.
Dr. Ross, your time is, you've reached your limit.
I know. Okay, so next week we're going to actually talk about what our supermassive black hole is doing in the past. We're going to talk about the local bubble, the local fluff, and then the amazing set of elements that we have today that exists on no other rocky body within the universe. And that will wrap it up. So next week for sure, we're going to wrap up the series, and then we'll launch a new one. So thank you for watching the clock, and I'll take questions. I'll take questions on any subject. And how about if we alternate between questions from the live audience and questions from the virtual audience? So those of you who are watching us through YouTube Live, feel free to submit your questions. We had a bunch from last time that we never got to, so we can tap into those as well. So how about if we begin with a question from the live audience, and we'll go to the virtual audience. And yes?
How does dark matter balance spiral arms?
Okay, good. That's another, okay, people ask me, how is it that our Milky Way galaxy is so different from all these other spiral galaxies? And yeah, why don't you repeat the question so we get it recorded?
How does dark matter play in between the spiral arm distance to balance them?
Right. I don't know whether I showed this last week or not, but I do have a map showing the distribution of dark matter in our Milky Way galaxy. And what's unusual about our galaxy, it's 10% ordinary matter and 90% dark matter. By ordinary matter, I mean matter made up of protons, neutrons, and electrons, the stuff we're made up of. And most of the ordinary matter in our Milky Way galaxy is dark. Only a small percentage of it actually is in the form of stars and brightly illuminating nebulae. The rest of it's dark, but it's dominated by exotic dark matter. That's matter that's made up of particles that do not strongly interact with light, and some don't interact with light at all. But we have this huge halo. And if I were to go back to this, here we go. Yeah, here we are, the local group. The dark matter halo that surrounds our Milky Way galaxy, it's so big, it extends halfway out towards the Andromeda galaxy. So we have this enormous, almost 2 million light year diameter dark matter halo. And it's because of that huge dark matter halo that we have this very stable spiral arm structure. It's one of the contributing factors. I mean, I was mentioning no collisions in the last 11 billion years of any consequence, but that dark matter halo plays a role as well. You say, what about the Andromeda galaxy? It's got an average dark matter halo, about 5 times less than what our Milky Way galaxy has. We don't know of any other large galaxy that's got such a high ratio of dark matter to ordinary matter. We do see it in these tiny dwarf galaxies, but we don't see it in any other large galaxy. And that's also one reason that we know our Milky Way galaxy has been eating on a regular basis these tiny dwarf galaxies, because those tiny dwarf galaxies are super endowed in dark matter. And so that's one of the sources for dark matter. But it doesn't account for all the dark matter. We got way too much dark matter. So that's still an unsolved problem in astrophysics. Where did our Milky Way galaxy, how did it get such an enormous halo in terms of its total mass and its broad extent? But it is a crucial feature to explain why we're here.
Okay. I'm going to jump ahead to a question that relates to your presentation
This is from the virtual audience?
from the virtual.
Okay, good.
Anthony Anuv. Why do astrophysicists see our sun as average and Dr. Ross doesn't? And he follows up with, for example, on PBS Spacetime just released a video, and they are adamant that the sun is very average.
The sun is very average in terms of its mass. I mean, if you look at the mass, there are stars that are 20 times, even 30 times the mass of our star, the sun. The smallest stars are 8% the mass of our sun. So the sun is, quote, average in that it's not very massive and it's not very light. It's kind of in between. It's middle age in terms of its burning. So it's kind of average. It's not very old. It's not very young. It's on the main sequence, which means it's still converting hydrogen into helium via the hydrogen bomb process. And that's where a good chunk of the stars in our galaxy, a small majority, are on the main sequence. So for all those reasons, our star is average, but for many other reasons, it's far from average. I mean, probably the most extreme difference is the composition. Our star, the sun, is a G5 type star, and there's lots of those stars in our Milky Way galaxy, but it has a unique composition. It's got an abnormal lithium abundance. It's called the Lithium Problem. How to explain why our sun has an abnormal abundance of lithium. And also, it has a shortage of refractory elements. And what we now know is what happened to the sun is that it, in its formation process, created 5 rocky planets, and these 5 rocky planets took with them a good chunk of the sun's refractory elements. I need to define that. A refractory element is an element that doesn't appear either as a gas or a liquid. So it's kind of like a solid substance, even at normal temperatures. And so the sun is deficient in those refractory elements. The rocky planets of the sun are superabundant in the refractory elements. And so the sun basically transferred a lot of its refractory elements to its 5 rocky planets. And what's also unique is that the sun's rocky planets are bigger than what we see around other G-type stars, and especially the planets are orbiting far away. I mean, one thing I'm going to be discussing in Design to the Core is looking at all the exo-rocky planets we've discovered. Rocky planets that are orbiting other stars. And what you'll notice is none of them orbit more distantly than Mercury. They're all inside Mercury's orbit relative to their host star. And typically with rocky planets, they are denser as you get close to the star for obvious reasons. The heat of the star drives off the light elements. What's unique about this is all stuff I'm going to be sharing next week, so maybe I'll stop right here. But that's what's so special about our star, the sun, is its composition and its rocky planets. It's got a set of rocky planets like no other, but hey, if we weren't on a big, dense planet far away from our host star, no advanced life would be possible here on Earth. And the rocky planets around the sun are unique. Anyone from the live audience, or you got another one from the virtual?
Oh, we've got more.
Oh, I'm sure you do.
Let's see, here's one from Scott. He says, or he asked, what are your thoughts on the privation theory of evil?
The privation theory of evil?
Yeah.
I wish Scott could amplify that question. I'm not sure what he's talking about. I mean, something in astronomy is called the axis of evil. He's probably not mentioning that. Is he talking something theological?
I think so. He just doesn't give enough details. Scott, if you're out there, send us another question, please.
And just give us a little background what you mean by the privation of evil.
Okay. Well, here's one from Doug McComb.
Okay, I don't know about the rest of you, but I don't think I'm too deprived of evil. How about?
Let's see. Doug asked, what is the prescription will of God? Another P question.
What is the prescribed will of God?
Prescription will of God.
Yeah. That's a theological term where people are trying to discern, okay, how do we define the will of God? How does God exercise his will? And does he control everything to a minute detail? Or does he allow us to exercise a fair range? In other words, does God play dice? And if he does play dice, to what degree does he play dice? It was Albert Einstein who said, God doesn't play dice, as a way to reject quantum mechanics. But later in his life he realized, wow, quantum mechanics really is true. So God does play dice, but he very carefully designs the dice. And what we now discovered is that, and I think this is relevant to the question, when we look at statistical mechanics and quantum mechanics, what we observe is that there is an allowed measure of uncertainty in the physics of statistical mechanics as well as quantum mechanics, and that permitted uncertainty that God put into both quantum mechanics and statistical mechanics is absolutely essential for life. So for example, without the uncertainty in statistical mechanics, there's motors, ratchet motors inside the cell that would not be able to operate. They operate according to Brownian motion, which depends on the uncertainty of statistical mechanics. So all those motors would fail to function and all life would die. And likewise in quantum mechanics, the Heisenberg uncertainty principle basically says if you choose to measure the energy level of a quantum particle to a high degree of accuracy, the uncertainty for the position of the particle will be about plus or minus a third of a mile. So the quantum uncertainty is large. Now in quantum mechanics, you can do the opposite. You can measure the position accurately, but now you've got an enormous uncertainty in the energy level. But what physicists have discovered is the degree of uncertainty is exactly what you need for proteins in our bodies. A number of your proteins act like transistors, and the transistor effect depends on the quantum uncertainty. So if we were to make the uncertainty more than, say, plus or minus a third of a mile on the position, those proteins would fail to function and you would die. Make the uncertainty less, you also die. It has to be fine-tuned. On that basis, the theological question, to what degree does God permit uncertainty in human affairs? Well, I don't have an answer for that. That's a good question to ask God when we meet him. On the other hand, if we use the analogy of what we see in quantum mechanics and statistical mechanics, maybe he does allow a certain degree of uncertainty, because that degree of uncertainty actually helps to fulfill its purpose. Beyond that, I would say to the Doug, I don't know.
Okay. Questions? We have another one from the audience. Oh, was there? No, okay, so
Yeah, go
an
for it.
online question. Someone named Slam RN.
Oh, I know who that is.
Okay.
Yeah, she's a nurse.
Oh,
RN stands for nurse. Susan
Okay.
Lambo.
Oh, that's Susan. Okay.
That's Susan, yeah.
All right.
Almost all of you know Susan.
She's wondering, relative to what? How do they define making a revolution around the galaxy?
Oh, well, we make measurements. So we look at other stars that are close to us and measure how fast they're moving. And if you make those measurements over the course of 100 years, you can determine how long it's going to take for that star to complete one orbit around the sun. So same way you determine the orbits of Mercury and Venus around the sun, you make measurements over a period of time, you use Newton's laws of motion, and you determine the revolution rate. In the case of Mercury and Venus and Mars, we actually get to see several complete rotations. I think what Susan's pointing out is astronomers have yet to measure a complete rotation around the center of our galaxy. We haven't been observing long enough to see that, but we observe enough of the orbit that we can calculate how long it'll take. Now, when I say 240 million years, we've not been observing the velocity of the Earth about the center of the galaxy long enough to give you a really accurate answer. When I say 240 million, that's 240 million plus or minus 4 million years. So hey, another century or so of observations, we'll be able to give you a more accurate answer.
Okay. Here's one from Jen, Ohio. What would you say when physicists say free will is an illusion? We really have no choice based on our genes and life experience.
Yeah, if you were to come up to my office upstairs, you'll see I got several textbooks, books written by scientists who are not theists. And what they point out is if there is no God, then we human beings have no free will. And I kind of agree with their argument. If you're going to claim that there's no God, that means there's no purpose for anything that exists in the universe. And therefore, where would free will come from? So they basically say everything is determined. If there's no God, then everything is determined by the laws of physics. And if everything is determined by the laws of physics, what we think is free will choices we're making are simply random choices that we're making. Not completely random, because our environment will determine which of the different options that we take. But if there is a God, then we can argue, hey, it's not just reaction to our environment. We're actually able to act independent of our environment. And there really is purpose. Once you establish that there's purpose of the universe, there's purpose for us humans being alive, that we really do an eternal destiny, then free will. And also, free will only makes sense in the context of the dualistic nature of us human beings. Namely, that we're not just physical beings governed by physics and chemistry and the laws of physics. In addition to our physical nature, we have a spiritual nature. And it's in the spirit realm where our free will exists. So I do agree with these scientists who say, if it's just physics and chemistry describes everything about our human existence, then we're fooling ourselves and thinking we have free will. But if we're dualistic, like the Bible declares, where we have a physical nature and a spiritual nature, then free will is not only possible, it's exactly what you would expect. Indeed, the universe is created by a personal free will being. If God has free will, it would make sense that his creatures that he's given a dual nature to also would have that free will. And I love what Ecclesiastes tells us. Eternity is written on our hearts. And purpose is written on our hearts as well. There's a video recording of a debate I participated in at Caltech, sponsored by the International Skeptics Society. And, what's interesting about that is they had 5 scientists speak before my debate. And all of them were atheists, but they all insisted that we human beings have ultimate purpose. And it's like, if there is no God, we have no more purpose than a rock does or a piece of dust does. But they couldn't deny this. They all insisted, yes, there is no God, but there's value to our lives, there's purpose to our lives, and there's a reason why we need to be morally responsible. And what they're really documenting is this. Even the atheists recognize that they possess ultimate purpose, that really God has written eternity on the heart of all of us, and that our lives don't end here. So just the fact that you see that inconsistency, even amongst the atheists, tells us there's something else going on. Yes?
Hugh,
have a
I'd like to
question?
follow up on that question, then I'll go down to the one up front. If the naturalists were right, and that we are just completely determined by the chemistry of our bodies, and that our minds would only contrive whatever random events would occur in our brain, then how in the world would there be any order to what we're thinking?
That's great, Mark, is that, and this is something my colleague Ken Samples, our staff philosopher, has written extensively about. If indeed we human beings are simply the product of chemistry and physics, then how can we trust what our minds are telling us? Our minds are simply the product of the random outcomes of physics and chemistry. So what makes us think that what we're discerning in our brain and our mind actually has any relevance to truth or reality? And again, when you talk to people who are atheist scholars, they all have this sense that they can determine truth with their mind, but if their mind is a product of physics and chemistry, natural process evolution, then who knows? So, again, we got books, not that we've written, but books that other people have written making that point. And Mark, this is kind of in your area, so if you want to make a comment, go for it. Okay.
I think this is like in one of the first slides or the second slides. You know how you were saying that like the funnels that are feeding the dwarf galaxies at just the right pace for it to like exist. So is there something that like slows that down or speeds that process up of how consistently they're feeding those dwarf planets?
You're raising an excellent point there about these large and small Magellanic Clouds that are funneling galaxies into our Milky Way galaxy. The funnel works right now. It's been working for the past several billion years. However, right now, the Large Magellanic Cloud itself has accumulated several dwarf galaxies, so it's gotten a lot more massive. Sufficiently massive that it's now headed towards our Milky Way galaxy's core. And so this funnel is not going to be optimal much longer. Now, when I say much longer, remember, you're talking to an astronomer. I'm not saying tomorrow it's going to collapse. Now, we're okay for a few million years. But 4 billion years from now, the Andromeda galaxy will merge with our Milky Way galaxy. And even 3 billion years from now, it's going to be close enough to significantly gravitationally distort our Milky Way galaxy. So yeah, it's going to be bad news in the future, in the far future. And if you go back into the distant past, then we know that the Large Magellanic Cloud wasn't close enough to us to operate as an optimal funnel. And also we need the combination of the Small Magellanic Cloud. And one of the figures that I'm going to have and designed at the core actually shows you a detailed map of the gas streams that the Large and Small Magellanic Cloud are funneling into the core of our Milky Way galaxy. It's important that the funnel be directed to the core of our galaxy rather than to the outer edge. But yeah, astronomers have actually mapped in detail how the funnel is working right now, and yeah, it really is a marvelous figure to look at to see how it's funneling everything in just right. I'll see if I can pull that figure up and put it into because I actually have the JPEG, I'll put it into the talk. So next week you can actually see that. But yeah, that's part of the incredible design feature. But you're right, it's a temporal design, but it's here at just the right time for us.
Do you want to follow up? Anything else? Okay. Thank you.
Hugh, I think that's it. We have no more questions. Or do you have one, Steve?
Just narrow if you can. Is there an RTB model that would show where in Genesis 1 that most of the super galaxies and so forth condense? If so, what day? Maybe not in a day. Just whatever you think.
Well, Steve, I'm actually coming with a blog article on a brand new paper just got published saying that when galaxies are forming and the larger galaxies are forming, you get this huge rush of matter coming into the center of these galaxies. And normally you would think that would cause a very rapid growth in the supermassive black holes. And indeed, we do see distant large galaxies with these quasars. A quasar is a supermassive black hole in the center of a large galaxy that's absorbing a lot of matter. That's why we can see them so far away. However, this new paper that got published says that these early galaxies are absorbing matter at such a high rate into their supermassive black hole that you get these powerful jets that eject the matter before it gets sucked into the black hole. You can see a little bit of that happening with the galaxy M87. I showed you the map of the supermassive black hole last week. It's got jets, and so these jets are actually blowing matter away from the supermassive black hole. That's kind of a wonderful thing. The supermassive black hole creates these jets, and yet the jets play a role in sending matter away from the supermassive black hole, so it's not eating too much. But this is something the James Webb Telescope is going to be focusing on, looking at these very first formed galaxies, as well as the first formed stars, to see what's going on there. But you're raising a good point, is that it's quite different in the first 3 billion years of cosmic history than it is today. And you got a comment?
Thank you. That's interesting. And let me refocus a little bit. Is there a correlation between what was just described and what is described in Genesis chapter 1 during any one of the creation days? Or would that be hard to make that correlation?
It'd be hard to make that correlation for the simple reason, at least in my interpretation of Genesis 1. Genesis 1:2, you already have the primordial earth. So you got 9 billion years between Genesis 1:1 and Genesis 1:2. And there's not much being said in Genesis 1:1 and 1:2 about what predated the earth. So in that sense, you got a lot of room. What I was sharing with you, however, is there is a constraint, because Genesis 1 tells us you wind up with human beings. And to wind up with human beings, you are going to have to fine-tune the behavior of galaxies before the earth is formed. So in this paper that just got published, I'm going to be writing a blog on, I'm going to be making the point, unless we had these powerful jets blowing matter away from the galaxies into the intergalactic medium, we wouldn't have the galaxies we have today, and our Milky Way galaxy wouldn't have the features that it has to make advanced life possible. So yeah, there are significant things going on there that the book of nature is going to tell us about, but nothing explicit in the book of Scripture, other than the fact that as you go on in Genesis 1, you got plants, you got animals, you got human beings, and for all that to work, that does put constraints on what happens in the first 9 billion years of cosmic history.
Hugh, Scott returned that question about privation theory.
Okay.
And he says, it's a theological question. It's the theory that there is no real evil, only an absence of good. It was promoted by several in the past, notably Thomas Aquinas and St. Augustine.
Right. I think now I know what you're talking about. It's the idea that evil doesn't really exist, but you have the deprivation of a good. And where I think that's contradicted, and it may be just the fact that people are writing at times in history where they don't see a lot of what I would call spite. I mean, this is something that is unique to the human species. We're the only species of life on this planet that exercises spite. And spite is a subcategory of evil where we do evil to one another, where the consequences of that evil bring great harm on the perpetrator of the evil. And this is what's weird, is that you really can't explain that by, say, Darwinian evolution, the survival of the fittest, because the one perpetrating this harm on other individuals actually winds up experiencing even more harm on themselves, which means it's not just the lack of good. There really is some evil going on here, where people are not behaving rationally. They're behaving very irrationally. I mean, I think we've got a good example of that right now with the Ukraine war. I mean, what Putin and Russia are doing in Ukraine is definitely counter to their best interests. They would have been far better off. In fact, I remember talking to national security experts a decade ago, worried that NATO wouldn't survive. I says, NATO won't survive if there is not a perceived external threat. And what the Russians wanted was for NATO to go away. All they had to do to have NATO go away is start behaving like a peaceful democratic country, and then there'd be no purpose for NATO. But now NATO is going to be around for a long time. So, and look at all the damage that the Russians are experiencing as a result of this ill-conceived war. But we've seen this in the past. We've seen this with Second World War, where you had Hitler doing things that were definitely counter to his best interests and the best interests of the German nation. Or to pick another Russian example, look at Joe Stalin. The fact that he murdered 20 million of his own citizens, definitely counter to his best interests. And also what you see documented by Solzhenitsyn is that a very high proportion of the people he murdered were the most competent and productive people in the Russian nation. The intellectuals were wiped out at a far greater proportion. And here he was facing Nazi Germany, and the generals were gone, his intellectual base was gone, the very people he needed, but they were killed. So, but the flip side of that is we humans are also irrationally altruistic. We do good to other people that has zero benefit for our own survival. Humans are unique in that we will show goodness and love to other humans that we'll never have any contact with, not even through our extended relative base. The fact that we will help people that are thousands of miles away, for which we have any kind of relationship with. So humans, as Pascal said, are inexplicably virtuous and inexplicably evil. So on that basis, quoting Pascal, there really is fundamental good and fundamental evil. It's not just the absence of good or the absence of evil. Although I would argue that there is absence of evil and absence of good. That really does happen, but it's not the whole story. At least that's my theology.
Right now, if you'd like to end us in prayer, we'd love you to wrap it up.
Be happy to do that. Father in heaven, we thank you for this technology where we can gather together in person, also include people from around the world through YouTube Live. And Father, I pray that we wouldn't just be receivers of your knowledge and truth, we would be sharers. So Father, I pray that you would give us opportunities to share what we're learning and understanding with others. And Father, that we would encourage one another and bless one another for what we're learning. And Lord, may we do it all in a spirit of love. Father, thank you that you're the source of all love. Help us to be a channel of your love. In Jesus' name, amen.